Hello, welcome to our talk on CyGIL, CyberGym for training autonomous agents over emulated network systems. I'm Li. I'm with Defense Research and Development Canada. This is a work with my co-authors Raed, Fayad, and Dr. Adrian Taylor. It's also work produced through collaboration with our international research partners in the ACD work group. We're looking at autonomous cyber operations that involve multi-stage sequential decision-making. Seems to be a good fit for reinforcement learning. It is envisioned that we may train the AI-capable Raed agents that may discover and reveal to us the hidden and emergent course of action of attacks so that we can improve the hardening of our network. And we can use that to even train our blue teams, for example, to train blue agents fighting against Raed agents to optimize their defensive decision-making. So the first question is to have a reinforcement learning training environment for it. The cyber operational networks are very complex, involves many different components, large numbers of parameters, a very large action space, and of course, state space. Usually the solution to build reinforcement learning environment is to do a simulation of the environment. It has a good advantage to reduce the state space, to reduce the complexity, to speed up the training. However, one question would be, a decision model trained in a simulating environment, how relevant it is when moving into the real network? A possible alternative would be, can we build reinforcement environment upon real networks and using real actions? For that, there are many emulation tools for both blue and Raed cyber operational teams. However, there are not so many reinforcement learning training environment built upon emulators. CyGIL is an experiment to build the reinforcement learning training environment for network cyber operations upon real networks using real state-of-the-art blue and Raed operational tools to form end-to-end kill chain action capabilities. Instead of simulating the system, reducing the action space and state space, we let it blow. Leave that complexity to the agent to deal with it. The current status of CyGIL, we have system architecture and code base for both blue agents and Raed agents, provide open AI gym standard interface for agent training, and have first testbed running with initial set of Raed training games. Therefore, the experiences and our observations results reported here are based on Raed agent training games. The CyGIL reinforcement learning environment consists of the target network, which is either a real network or an emulated network on virtualized hardware resources. It also have the cyber operational command and control center. Here with the Raed agent perspective is the attack C2. The Raed agent is at the attack C2. It mobilizes its implants, we call it hands, in the target network to execute actions and to achieve its campaign objective. The CyGIL environment starts when at least one hand is deployed in the target network. So the environment needs to wrap up this whole system into an open AI gym standard Python class. We do this through three main functional substrates. The first of them is network cyber physical system that wraps up the network and all its cyber assets. Then the action actuator would implement action upon the network. The results would be formatted by sensor views towards the agent in observation space, in rewards obtained, in game end flag, if any, and upon query, it also returns action space to the agent. So how we implement it? Through leveraging the state-of-the-art frameworks and tools. The networked cyber physical system consists of network hardware software assets. It provides interface for actions to be executed. It also manages training episodes. We use MITRE and ONUS SDN to emulate the network upon VMs. After evaluation of different red and blue cyber operational tools, we select MITRE Cadera because of its good coverage of the entire MITRE attack framework, TTPs, and also its execution staging capability. We build episodes management, leveraging Cadera's operation sequence management. For the action actuator, Cadera also implements all the action execution and parser function to parse the output results. So we use Cadera and build reward calculator on top of it. And then the sensor view is basic to format observation space action results in the standard interface towards the agent. So the red observation space is realistically just the output of red actions. It's command execution, basically. The red action space consists of more than 270 Windows actions and 180 Linux TTPs form the entire kill chain. Well, phase 2 and 3 of kill chain. We're also porting Metasploit via Cadera plugin. It's also possible to implement and improve TTPs through Cadera's plugin. The game design details are beyond scope of this paper. In summary, an environment instance consists of the network scenario and game designed upon it. Multiple games can be designed for a single network scenario. A game is defined by initial position of the hands, action space, reward function, and the game end criteria. All of them can be configured. The reward function used in the examples in this paper are simple, objective-oriented reward function. It gives a negative reward representing cost for each step until the final step of the objective of the game. Like you win the game, you get the positive reward. This pushes the agent to go as fast as possible to reach its objective, and also to prevent any kind of human experts influence or hints in the middle, to leave full potential to the deep learning model on the agent side to make a decision. We also provide a maximum number of steps reached as the game end criteria. Then you can run a game without a single objective, but just spend the time. So the CyGIL testbed setup consists of two parts, the network node and CyGIL node. They are not just single node. Each of them can scale up to servers all the way to cloud infrastructure independently to improve scalability and to provide power. In the minimum setup, network node is on one laptop and CyGIL node is on the other laptop. The network node consists of the emulated network running on VMs. The CyGIL node provides the CyGIL environment library. We also run the agent training algorithms on the CyGIL node. We're currently moving the environment setup into the lab. The first game is a simple game of file exfiltration. The objective is to steal the file. The agent wins when it mobilizes the hands to ship all the stolen file to the C2. The network consists of 4 hosts with traffic going between them, including both the Windows hosts and Linux hosts. The optimal COA is kind of simple, but the agent has to figure out the steps. We tested using both the TensorFlow and PyTorch platforms framework, running DQN and the cross-entropy algorithm. Simple algorithms, both of them can train the agent to achieve the optimal COA. The second game is a little bit more interesting, consists of 10 hosts in a network where the Active Directory server is hosted on host 9 with domain controller. The objective for the Raed team is to capture the domain controller because you need the domain privilege to capture the domain controller that represent a major breach of the system. The initial hands sitting on host 2, the agent need to mobilize hands to discover where the domain controller is, how to reach it, where to escalate privilege, where to steal the domain admin's secrets. There are several potential and several optimal course of actions. this is a little bit more complex game, also because of realistically low successful ratio of certain actions, for example, lateral movement, and also privilege escalation. We tested DQ and reinforced PPU, all these classic algorithms. The agent did get trained to reach the optimum course of action, but it is a more complex game and take longer time. Okay, the latency issue for an emulation-based environment. Latency consists of both the action execution latency per step and also the game end absolute resetting for the new game, the reset latency. For action execution, latency ranges from less than 1 second to several minutes. This is most because of waiting for the beacon to report back at C2, because the implant, the hand needs to, for example, in lateral movement, needs to land onto a remote host and report back amid all the network and user traffic. It incurs the delay. The resetting, we do both cleaning and VM resetting. This takes on a single laptop hosting Game 2, which has 12 VMs. It takes average of 70 seconds. When we upgrade from VMware Workstation to the enterprise level vCenter and vSphere interface, we reduce this to a couple of seconds, but needs further test to solidify that option of implementation. The agent total training time for Game 2, for example, takes a few days, all the way to about a week. This is long, but still may be favorable compared with real red team exercise, which takes usually several weeks to a few months to complete. In summary, in CyGIL, we experiment reinforcement learning environment upon real cyber networks and using the cyber red blue tools directly. We find it is actually quite simple in terms of system design because it is stateless. So we don't have to build a complex simulator to capture the system. The system runs by itself. And the training is possible for the algorithms. However, latency is an issue. Current and future work, we're improving the testbed scalability, reduce the latency, and also looking at game design, because the game design is a very interesting problem. For the RL algorithm, the research is very focused on reducing the training time required to come up with more efficient algorithms. That's all for my presentation. Thank you for your attention, and I would like to welcome your questions. Thank you.